Hello students, welcome to AIMS India online courses. This is a chemistry session. In this we are discussing about the chapter structure of atom. In this session we are going to see about quantum mechanical model of the atom. In this about quantum numbers and atomic orbitals we are going to discuss. Called Max Planck was a German theoretical physicist who organized quantum theory, which won him the Nobel Prize in Physics in 1918. Actually, Max Planck made many contributions to the theoretical physics, but his fame rests primarily on his role as originator of the quantum theory. Yes, actually, he made so many contributions in theoretical physics, but his work on quantum theory kept him idle and it won the Nobel Prize for him. This theory was revolutionized human understanding of atomic and subatomic processes. Yes, after this theory, the idea of atom was changed completely. In understanding of atomic and subatomic processes, the idea and view was changed. If the electron revolves around the nucleus in definite paths or orbits, the exact position of the electron at various times will be known. Yes, if the electron is revolving around the nucleus in the definite path or orbit, then the exact position of the electron at various times can be known or will be known. For that, we have to answer two questions to find the position of the electron at various times. We should know answers for two questions here. One it is, what is the velocity of the electron, and is it possible to find the exact position of the electron? May not. Electrons are invisible to naked eye. Then how do we find the position and velocity of the electron? Yes, it is an important question here. If we are trying to find the velocity and position of an electron, how is it possible? First of all, these electrons are microparticles which are very small, which cannot be seen with the naked eye. So then how to find these velocity and position of the electron? Generally, to find articles during dark nights, what do? We take the help of torchlight, isn't it? In the same way, we can take the help of suitable light to find the position and velocity of an electron. As electrons are very small, light of very short wavelength is required for this task. Yes, as these electrons are very small particles, a light of very short wavelength means with a high energy should be used for identifying these electrons in the atoms. The short wavelength light interacts with the electron and disturbs the motion of the electron. And this is one more problem here. Actually, electron is revolving with the high velocity around the nucleus we are considering. To identify or detect it, if we use a light of high frequency or short wavelength, then what happens? This light will fall on the electron and it will interact with the electron and disturbs its motion, isn't it? Hence, simultaneously, the position and velocity of an electron cannot be measured accurately. So this is the problem. Actually, without disturbing the electron, just if we pass on to that light, we may detect its position or velocity exactly. But what happens when we pass certain light onto the electron? That passed light may interact with the electron and there may be change in the energy of the electron and hence it disturbs the motion of the electron. So if we calculate the position and velocity simultaneously, there may be some changes, errors. Hence we can say simultaneously the position and velocity of an electron cannot be measured accurately. If we measure, we get some errors. Okay. From this discussion, it is clear that electrons do not follow definite paths in an atom. If the electrons are not disturbed in orbits around the nucleus, this means that An atom does not have a definite boundary as suggested by Bohr's model. Yes, if electrons are not disturbed, then we can say there is no definite boundary in the atoms as suggested by Bohr. As a result, it is not possible to pinpoint an electron in an atom. So from these all discussions we can say it is not possible to point out or pinpoint an electron in an atom at an exact position. So under these all circumstances, in order to understand the properties of electrons in an atom, a quantum mechanical model of atom was developed by Erwin Schrödinger. So to overcome these all limitations, to overcome these all circumstances, to find out the properties like position and exact position and velocity of an electron, a quantum mechanical model was developed by the scientist Erwin Schrödinger. According to this model of an atom, instead of orbits of Bohr's model, the electrons are thought to exist in a particular region of space around the nucleus at a given instant of time. Yes, actually, instead of orbits, just like in the Bohr's model, the electron he thought that electrons are thought to exist in a particular region or space around the nucleus at a given instant of time. So instead of pointing it out, the certain region or place is considered where electron can exist. The region of space around the nucleus where electrons probability finding is maximum is called an orbital. So in his model, Schrödinger considered a particular region where the probability of finding electron is being maximum. Instead of pointing it out at a particular position, he considered certain region or space. So the region of space around the nucleus where the probability of finding the electron is being maximum is called an orbital. In a given space around the nucleus, only certain orbitals can exist. Yes, in all the spaces electrons are not existing. In certain spaces only electrons finding probability is being maximum. Means orbitals are existing in few only certain orbitals. Each orbital of a stable energy state for the electron is described by a particular set of quantum numbers. So, so each orbital in any energy level is described by particular set of quantum numbers. Let us see here about these quantum numbers. What are these quantum numbers? How they are determined? As we know, to reach or to search a particular person in this world, four things are needed. What are those? The country to which the person belongs, the city in that country to which the person belongs, the street in that city where the person is residing, the house number. So if we know these 4 points, four things, we can reach that person or we can search a person in this world, isn't it? In the same way, similarly, four identification numbers are required to locate a particular electron in an atom. These set of identification numbers are called as quantum numbers. So now let us see what are these set of quantum numbers. Out of these four, the first one is principal quantum number. It was suggested or given by Niels Bohr. It is denoted with the symbol small n. It represents the name, size and energy of the shell to which the electron belongs. So it represents the name, size and energy of the shell to which the electron belongs. See here, it is denoted with the symbols 1, 2, 3, 4 and so on, or K, L, M, N and so on. So in this way it is denoted. Now as the number of the shell increasing, energy also will be increased, which is associated with the electron in that orbit. So the values of n are taken like this 1, 2, 3, 4 and so on until infinity. So as per the number of the shell, it is denoted with some symbols here. First shell is denoted with the K shell, second one L shell, third one M, N, O, P, Q, and so on. In this way, shells or orbits in an atom are denoted. In these orbits, electrons are revolving around the nucleus. Okay, these shell number or shell name gives even the energy of the electron associated with that shell. Higher is the value of n, greater is the distance of the shell from the nucleus. Yes, as our n value increases, the distance from the nucleus also increases for the electron, and the greater is the magnitude of energy. At the same time, distance increasing, at the same time energy of the electron also increases as n value increases. That means shell value increases. Okay. Energy separation between the two shells decreases on moving away from the nucleus. Yes, it is one more point to be considered. Don't be confused here. As the distance from the nucleus increases, energy of an electron increases. At the same time, the distance between the two adjacent orbits decreases as we move away from the nucleus. That means if you see here, the energy difference between first two orbits is greater than the next two, and it decreases as we move away from the nucleus. Okay, energy difference decreases, but energy of the orbits will be gradually increasing. Maximum number of electrons in a shell is given by the formula 2n square, where n represents number of the orbit. So if we substitute the number of the orbit, we can find how many electrons can be accommodated in that particular orbit. Okay. Next quantum number, azimuthal quantum number or angular quantum number also it is called. It was proposed by Sommerfeld. It is also called angular quantum number or a secondary quantum number. It is denoted with the symbol L. Its values are lying in between 0 to n minus 1, where n is principal quantum number. Okay, its values will be in between 0, 1, 2, 3 till n minus 1, where n representing the principal quantum number value. It describes the shape and the name of the subshell associated with the main shell. Yes, here first quantum number is representing the main shell in which electron is located. But in that main shell again, there might be different number of subshells. So in which subshell this electron is located is denoted by this azimuthal quantum number value. By knowing the azimuthal quantum number value, we can find out the subshell in which electron is located in that main shell. See here, L values will be like this. If L value is 0, that represents S subshell. If L value is 1, that represents P subshell. If it is 2, D subshell. 3, EF subshell. If it is 4, G subshell. In this way, based upon the value given for L, the subshell name and the size, shape of the subshell is determined. We know S subshell represents spherical shape, and L is equal to 1 means P subshell, that means dumbbell shaped orbitals. And if L value is 2, that represents D subshell, that represents a 4, actually here double dumbbell shape it is called. This represents subshells or orbitals with a double dumbbell shape. If L is equal to 3, that represents F subshell. The shape of a subshell is a four-folded or complex shape it is called. In this way, the shape of the subshell in which electron is located can be identified based upon the azimuthal quantum number value or L value. Okay. The energies of the various subshells in the same shell are in the order of here. S subshell has lowest value, and then P, D, F, G and so on. Increasing order it is shown here. So even though these subshells are present in the same shell or same orbit, there will be slight changes in their energies. S subshell is having lower energy among all the subshells in a orbit, and then P, and then D, and then F. In this way, energies of the subshells are in the increasing order. even though they present in the same shell. Okay. Maximum electrons present in a subshell is given by the formula 2 into 2l plus 1, where L is a azimuthal quantum number value. If you say yes subshell, what did we say L value for this? 0. So if you substitute 0 in this formula, what do we get? 2 into 0. It becomes 0 here. So plus 1. Totally it becomes 2. So the maximum number of electrons that can be accommodated in the S subshell is 2 electrons. If it is for P subshell, we know P for P subshell L value is 1. If we substitute 1 in this, we get it as 2 plus 1, 3. 3 into 2. Totally it becomes 6. So a P subshell can accommodate totally 6 electrons because there are 3 orbitals in it. Next, D subshell can accommodate totally 10 electrons if we substitute 2 in this formula. If we substitute 3 there in that formula, we get 14 for F subshell. In this way, the maximum number of electrons can be accommodated in a particular subshell is given by the formula 2 into 2l plus 1. So, S, P, D, F, G are spectral terms and signify. Yes, here we are using the names for these subshells S, P, D, F and so on. So these are signifying here. S signifying sharp, P represents principal, D represents diffused, F representing fundamental and G representing generalized respectively. So they are the names signified here based upon these symbols. Okay. Next, third quantum number, magnetic quantum number. It was proposed by Lande and it is denoted with the symbol M. It describes the orientation of the electron around the nucleus or orientation or distribution of electron cloud around the nucleus. Means in which direction these electrons are revolving around the nucleus is given by magnetic quantum number, that we say as orientation. Orientation of the electron is given by magnetic quantum number. For each value of L, the magnetic quantum number M may we assume all integral values from minus L to plus L including 0. So totally it will take the values 2L plus 1 values because it is taken from minus L to plus L including 0. All these integer values are taken by this. So M values are from minus L to plus L including 0, where L representing azimuthal quantum number value. So how many values for each azimuthal quantum number we are getting here? Magnetic quantum numbers 2L plus 1. Thus, when L is equal to 0, M is equal to also 0. That means only one kind of orientation. That means each orientation is called here orbital. So only one orbital is present in S subshell. Only one value. M value is only 1. Because here L value is 0. Then M values we are taking minus L to plus L including 0. L value itself it is 0. Some M also will be 0. Then only one orientation. The number of values obtained here for M gives a number of orientations. As M value only we are getting one value here, that is 0. So only one orientation is possible in that we say as S orbital or one orbital. Okay, each value of M representing one orbital. If when L is equal to 1, then what will be the M values? Minus L to plus L including 0 means minus 1, 0, plus 1. So three orientations are possible. This each orientation is considered as one orbital. Now in L is equal to 1 subshell, that means in the P subshell there are 3 orbitals. Okay, in this way, three kinds of orientations are possible. Each one is there in one direction. One is according to X and according to Y axis, and other one according to Z axis. In this way, three orientations are possible in the P subshell. Okay, next one, if we see the D subshell, that means L is equal to 2. Then M values will be minus L2 plus L including 0. That means minus 2, minus 1, 0, plus 1, plus 2. 5 values are possible. That means 5 orientations are possible in the L is equal to 2 subshell. That means D subshell. So we can say here L is equal to 2. That is D subshell contains 5 orientations. Each orientation is considered as one orbital. So we can say D subshell contains 5 orbitals. In a similar way, if you say L is equal to 3, what will the M values? Minus L2 plus L including 0 we are telling. So we can say here minus 3, minus 2 till plus 3 including 0. Totally we get 7 values or 7 orientations. So we are telling here each orientation representing one orbital. So L is equal to 3. That means F subshell contains 7 orbitals. Okay, each orientation corresponding to one orbital. Thus, the number of M values indicates the number of orbitals in a subshell with a particular L value. Orbitals. We are using the word here orbitals. What does it mean? At the starting in the quantum mechanical model initiation, it is used the word orbital. The places or the regions where there is a finite probability of finding electron around the nucleus are known as orbitals. So the places or regions around the nucleus where there is a finite probability of finding electron are called orbitals. See here, the outlines of orbitals are shown here. S orbital is in the spherical shape, and p orbitals are in the dumbbell shape in 3 orientations. Dumbbell shape it is called p orbitals. And if you see d orbitals, four-fold double dumbbell shape it is called. Means 2 dumbbells are existing in this 4 loops totally. Okay, 5 orientations are possible in this d orbitals. Only one is being different among the all, that is dz square, because it contains only 2 loops and there is one collar type neck at the middle. Okay, if you say f orbitals, totally 7 types of orientations are possible. Those we call as 7 orbitals. The shape of these are taken as 4-folded shape or a little complex shape. Okay, these are the shapes of the orbitals existing in the subshells. Next one, spin quantum number. It was proposed by Uhlenbeck and Goudsmit and it is denoted the symbol small s. Spin quantum numbers represents the direction of electron spin around its own axis. So the first quantum number, principal quantum number, indicates the shell in which electron is revolving around the nucleus. And the second one, azimuthal quantum number value, representing the subshell in which that electron is located in the shell. And third one, magnetic quantum number. It is representing the orientation of the electron around the nucleus, means in which orbital is located in the particular subshell. So first shell and subshell and in that again orbital. These were represented by those 3 quantum numbers. By coming to spin quantum number, it is giving the information about the self rotation of the electron around the nucleus. It is revolving around the nucleus. At the same time, it is having self rotation also. Okay, that self rotation of the electron is given by this 4th spin quantum number. That means either this electron is revolving the clockwise spin or anti-clockwise spin. The self rotation of the electron is given by this quantum number. So for clockwise spin of the electron, it is represented with the symbol upward arrow mark and its value is given as plus half. For anti-clockwise spin of the electron, the symbol given as downward arrow mark and its value is taken as minus half. Okay. See the overall picture of the quantum numbers. So first, the shell or the orbit is represented by the first quantum number, principal quantum number, that will contain different subshells again. So those subshells are represented the azimuthal quantum number 0, 1, 2, 3. 0 means S subshell, 1 means P subshell, 2 means D subshell. So in this way, subshells are represented with azimuthal quantum number L. In the subshell again there are different orbitals. If you see a subshell only one orbital, and p subshell 3 orbitals px, py, pz. If it is d subshell again 5 orbitals. Okay, in this way as a subshell value increasing, number of orbitals in that also gradually increasing. These orbitals are given by or informed by magnetic quantum number value m. In that orbital again, there will be two electrons in each orbital. In this orbital, there may be two electrons. In this also two. In this also two. In each orbital, there will be accommodation for two electrons. Those two electrons will be the different spins. One with the clockwise spin, the other with the anti-clockwise spin. So this self spin of the electrons is given by fourth quantum number, that is spin quantum number. So by knowing these 3 or 4 set of numbers, we can identify an electron in a particular atom. So in which shell it is there, in that shell again, in which subshell it is present, in that subshell again, in which orbital is present, in that orbital, which kind of self rotation it is having. So if you know these all, we can locate an electron exactly in the atom. Okay, this is about the 4 quantum numbers. Thank you for watching our video. Please subscribe our YouTube channel Aims Today for latest updates and recorded videos.